Hello, my name is Cameron Sabat, and this is Cutting to the Case with Dr. Timothy Joe. Dr. Timothy Joe is a distinguished professor, entrepreneur, and technology innovator with a career spanning startups, academia, and leadership in cloud computing. He was the first president of Oracle's cloud computing business, where he helped shape one of the foundational platforms for enterprise software in the cloud. After leaving Oracle, Dr. Joe returned to Stanford University, where he launched the first course in cloud computing, CS 309A, a class that has since featured guest lecturers from over 100 cloud public company CEOs. Inspired by the limitations he encountered in how medical data is shared and used, especially in pediatrics, Dr. Joe came out of retirement in 2020 to found Pediatric Moonshot. The mission of this initiative is ambitious: to reduce healthcare inequity, lower costs, and improve outcomes for children locally, rurally, and globally by creating privacy-preserving, real-time AI applications with access to data from 1 million healthcare machines across 500 children's hospitals. A key part of this mission is the development of BevelCloud, a decentralized in-building edge cloud infrastructure designed to allow AI applications to safely access data like imaging, EMR, and monitoring devices in real time, while preserving privacy, security, and data sovereignty. Over his more than 30 years in teaching in industry, Dr. Joe has also served on boards of public companies like Teradata, chaired accelerator programs like the Alchemist Accelerator, and written about the future of software and the industrial Internet of Things. Today, he's leading Pediatric Moonshot as beyond a technological venture as a global effort, really, to bring expert level pediatric care to underserved areas and to build the infrastructure that enables AI to make a meaningful difference in child health. Thank you very much, and thank you for joining.
Wow, Cameron, that was a heck of an intro.
I
I couldn't have
appreciate.
written it better myself.
Oh no, no. Thank you so much for joining. I mean, your presence is truly honored on this podcast. So, really, I wanted to dive right into the genesis of Pediatric Moonshot. What specific experiences or data motivated you to design this? And was there a moment you realized that current systems were fundamentally inadequate for pediatric care?
Yeah, well, as you mentioned, I went back to Stanford to start a class on cloud computing, and it's there that I have a strange student who turns out to be the head of pediatric cardiology at Children's Hospital of Orange County.
Hmm.
And Anthony, I like to say, is my portal into their world. So I'd never spent any time in healthcare until like 4 years ago. And so he showed me that, oh, yeah, they're still using CD-ROMs. And I'm going, are you kidding me? And then, today everybody knows this, but then people didn't realize that in order to build accurate AI algorithms, the only way to do that is you have to have access to large quantities of training data. So I'm looking at this, it's around COVID time frame. I'm thinking, oh, sit around and watch Netflix all day, or maybe we can do something useful. And so I got a group of engineers together with a mission, which you read, to really fundamentally transform children's healthcare using AI applications, real time AI applications, based on access to data in all million healthcare machines on all 500 children's hospitals in the world.
Absolutely. And what a laudable mission too. Um, Now about you're very technologically oriented. You're perhaps the most technologically oriented person we've had on the podcast so far. Can you walk us through the design and function of BevelCloud and the edge cloud's infrastructure you've built? And why do you believe that decentralized in-building architecture is crucial for real-time pediatric AI applications?
Yeah, so let me start with so that your listeners think about it. The way in which AI, as you experience it today, and I'm just going to use ChatGPT, although you could talk about Claude or anything else, is well, how did ChatGPT learn what it's learned?
Hmm.
Well, the answer is what you do is you bring a lot of training data into a central location. Many of your listeners have heard about people building big data centers and tech computers at it to, in essence, learn on that data. It is, in essence, for people interested, go look up neural networks. It's, in essence, we'll call it a trial and error method by which you create a neural network which, quote, learns off of this vast amount of, we'll call it text data. Okay. So that's kind of how it works. But we felt like this is never going to work in healthcare and life science because, number one, these data sizes are much larger. Ultrasound studies are a terabyte. Uh, that's not a New York Times article, right? A terabyte. The security requirements much tougher. Privacy requirements much more strict, right? Norway says we do not want Norwegian data leaving Norway. Actually, 3 states in Australia have different privacy laws. So we said, look, this is computer science 101. Rather than move the data to the application, let's move the application to the data. So this is why we engineered a distributed AI cloud infrastructure, which literally puts a cloud server inside the building at a clinic, at a research lab, at a hospital. So you go, why does it need to be in the building? Well, remember I said we want to build real-time systems. And the only way that you can get real-time data from that ultrasound or blood analyzer or gene sequencer, whatever, is on the network there. So engineering the ability to go do that
Mhm.
managed on a global basis is obviously the technical challenge. But the reason for doing this is that in the end, there's vast amounts of training data. We've done a back of the envelope analysis. The 500 children's hospitals in the world generate 6 million terabytes of data a year. Now, you think about what we could train just in cardiology on that amount of data. It's You could think of anything and everything, but you're never going to be able to do it by trying to move 6 million terabytes to Texas.
Mhm. Yes, yes, absolutely. Yeah, it's impossible, and that's why you need kind of BevelCloud and this cloud infrastructure built. I
Yes.
appreciate that. Yes, and as you're doing that, um, you really do speak of rural areas, underserved global regions, and places without those pediatric specialists. How do you plan to scale Pediatric Moonshot to make sure that those places truly benefit, you know, in measurable health outcomes, not just in theory? Because a lot of these new
Yeah,
technologies
no,
are deployed.
yeah, well, that really was kind of in the end, the motivate it. People don't realize this, but 60% of the rural counties in the United States have zero pediatric expertise, none.
Mhm.
So you kind of go, while we can debate whether AI is better than the world's best pediatric oncologist or whatever, I think you can easily argue that AI technology could be better than nothing, which is really what's going on in most of rural America's world, right? And we built an architecture that was deployed from day one on a distributed basis. So actually, our servers can run inside an ambulance. So now you can, if you think about it, I can now create an application with the best and brightest pediatric orthopedic experts and now put that in as an application, which is running in an ambulance, running in a clinic, running anywhere in the world.
Mhm.
I mean, we've done it, just for people to think about it. That's happened in the world of mobile computing. I built a really cool ride sharing application, and now everybody in the world gets to use it. Why can't we do that for cardiology, oncology, orthopedics, et cetera?
Sure, sure. Yeah, I definitely see the vision. And, as I'm thinking about this, I'm thinking about technical challenges as well, in terms of data standardization and quality, not just privacy concerns as well. With machines from different manufacturers and you have imaging devices, blood analyzers, EMRs, how do you standardize data like digital twins so that AI models trained on them are accurate, reliable, and generalizable?
Yeah, so we kind of came at it, which is kind of generally how we think about this from the bottom up. So
Mhm.
if you have this is use the road analogy, you need a good foundation in a road, otherwise nothing else works. So good foundation. What's a good foundation? I've standardized compute, standardized storage, standardized networking everywhere. I get that good. Okay, you just said it. How do I now build a digital twin
Mhm.
of that ultrasound. And so what we're doing right now is we're building digital twins by machine class. So there's a Philips digital twin that runs everything from their portable Lumifies all the way up to their big Epic 7s. What that means is that I don't care where in the world those machines are, the data presented to the application is identical,
Mhm.
right? And for imaging, because of a lot of standardization, DICOM, et cetera, that's pretty true across lots of different imaging machines, imaging types. Now let's go to something more difficult, a blood analyzer. There's a Siemens blood analyzer and a Beckman blood analyzer. The, all we're going to say is, look, we'll standardize the data so that every Siemens blood analyzer will deliver the data to the application the same way everywhere in the world. Same with the Beckman blood analyzer, everywhere in the world. Then we're going to leave it to the application to go, well, field 3 is the same as field 7 or whatever it is,
Mhm.
right? To be able to abstract, to your point, the different things that each of those machines might indeed do. So we're going to try to standardize at the lowest level that we can
Mhm.
and then make it, I'll call it an application question of how it wants to deal with the differences between those.
Yes, yes, absolutely. And really, um, once, looking ahead 5 or 10 years, once the pediatric moonshot achieves its goals, not if, what will pediatric healthcare look like globally? And what would you want children, clinicians, and systems in remote or underserved, under-resourced areas be able to do that they currently can't?
Well, I think it could be there. A lot of this stuff isn't really that hard. It's just
Mhm.
we've never built an infrastructure to do this. So I'll give you number one. This happens at this very moment. There is a hospital in Willits, California, population 5,000, that 20 times a month they send a kid to UCSF, Stanford, Shriners Burn Unit, or UC Davis. Why? Because they have no pediatric expertise whatsoever. Now, we've talked to the folks at Texas Children in the emergency room, and they go, well, if we could have seen the image ahead of time, we could have told them there's really no need to send the kid. So that's like super hyper simple, right? Okay, let's go to another level. We just saw this actually occur in Southern California. Kid comes in to the emergency room. He's been hit on the head. They go MRI image him. They go, doesn't have a concussion. They send him home. 6 weeks later, he goes to another hospital, re MRI image him, and they went, nah, he doesn't have a concussion. Weeks later, he is at a third site. They MRI image him. They go, he has a brain tumor, right? So, and they eventually looked at the original MRI image and it was there.
Mhm.
So now you can imagine why can't we build applications which in real time look at an MRI image and say red, green, yellow, hey, this kid has a brain tumor or everything's okay, or somebody ought to look at this because as we all know, there's human confirmation bias everywhere. So I think what you could start to see to me is trying to solve some of these really simple problems all the way to this is what we're working on right now is we're now tracking about 80 different rare diseases in children for which there are therapeutics. The wonderful side is the biopharma industry is creating more and more specialized drugs for more and more special conditions. The giant question is great, I now know I have a therapeutic for it. How do I know if the kid has it? And so, again, you can now start to imagine AI agents. We're working on these, we call them disease precise AI agents, which use multimodal biomarkers to walk through the EMR all day, all night, grading every patient and going, nah, it doesn't have FSGS or IgAN or any number of different conditions. And for the few, hopefully, it waves its hand and says, look, here's 34 reasons why I do believe this kid has this condition. I mean, the cognitive load at this point for any physician in terms of all these different therapeutics, both, those that are taken by mouth, those that can be done through devices, is enormous.
Mhm.
We can use computers to vastly change the dynamic of that. And most importantly, do it on an equitable basis. I always say, hey, if your mom works for Google and you live in Palo Alto, yeah, what we're working on is kind of interesting, but that's not most kids in the world. And I think technology has the capability to provide much better service, much lower cost across large patient populations.
Absolutely. Yes. Yes. And moving from patient populations as well to our podcast population, I wanted to, I always close out my podcast episodes with a final question for the audience, which is if you had some advice for medical students who want to um, have the level of impact that you're having throughout the course of their careers, what would you suggest to them? What are some concrete steps?
You're not going to like my first answer.
Is it to leave medical school and just to start working in this? No.
No, I sometimes kid medical school students. I said, you go be a physician and affect, I don't know, 10,000 people, 50,000 people, 100,000. If you start building software, it affects millions and billions of people.
Mhm.
So the thing I would say to all of them is, yes, we do need physicians. I'm not telling you to leave medical school, but I would encourage you to learn our language. I think at the end of the day, we, the tech community, needs to learn your language. You need to learn our language so that we can work together. Because at the end of the day, yes, we're building incredible infrastructure to do amazing things. But tell you the truth, Cameron, I have no idea what FSGS is or IGAN or, tetralogy of Fallot. I mean, I've heard all these words. I can say the words. I have no idea what they are.
Mhm.
But can I converse with a pediatric cardiologist or an oncologist? I think I'm getting better at it, is what I would say, because I'm starting to learn some of the words, right? But I would encourage the other half of it, which is I'm not asking you to go be a programmer or anything, but I am asking you to learn what are these fundamental ideas in software, in neural nets, et cetera,
Mhm.
so that as you go out there, you can effectively work in teams and develop the applications that'll change everything no matter what specialization we're talking about.
Sure, sure. No, I very much appreciate that, and I've taken that to heart, quite literally, and a lot of my colleagues have as well. I've been kind of spreading that among my own medical school colleagues. I have a couple friends from MIT and Stanford who've gone to medical school, and we operate in the same research groups, and we
Mm-hmm.
do a lot of very interesting work together, both through coding infrastructure, apps, and doing research. So I mean, thank you very much for sharing that. A lot of people look up to you. And so, watching this podcast might inspire some people to pick up some programming on the
Good,
side as well. So, yes,
good.
thank you very much for joining Cutting to the Case.
Well, and Cameron, thanks for doing this. I love your mission for your podcast. Keep it up.
Absolutely. Trying to reach as many people as I can. So feel free to spread the word, share it with anyone you want, both the audience and Dr. Joe. And yes, thank you very much. This is Cameron Sabat signing off.